Hello everyone, good morning. I'm Khushboo Suman, and just like coffee, I'm a freshly brewed faculty in the Department of Chemical Engineering at IIT Madras. So thank you to the organizers for giving me the opportunity to speak here and network with people here because I'm new to this area and happy to meet everyone. So today I'm going to talk about my work on dynamic arrest of adhesive hard spheres following a thermal quench. And before diving into the topic, I'll just give a brief overview of what I have been doing and then dive into the topic. Okay. So I can broadly categorize what I have been doing over the past few years in these four categories. So I've worked mostly on gel-like systems. So now these gel systems can gel on response to time or temperature, and the systems which gel with respect to time are called as a spontaneously gelling system. With respect to temperature, we call it the thermoresponsive gel systems. I also worked on synthesizing some systems or nanoparticles of spherical shape and of rod-like shape, and some part of my work was also on industrial collaboration where we worked on some industrial projects. So we had few publications and few of the problem statements which we tried to address. So to begin with, we worked on the spontaneously gelling system where we had a model system of laponite, which is a clay particle of anisotropic shape, a disc-like shape, and we tried to understand different facets of gelation through this model system over here. We developed a phenomenological model to understand how the gel would behave in the different stages of gelling, and we developed the model for the same, which is a brief result is represented over here. We also worked on an experimental plus theoretical work, which would be to predict the time to gelation for any system. So with just some little knowledge about the system, you will be able to get a priori a knowledge about how much time will system take to gel. And that was another part of the work which I did. We also worked upon the thermoresponsive system, where the agenda was basically to understand the phase behavior of the system, and we found that one of the thermoresponsive system underwent a very beautiful gel to glass-like transition, which was something unique to be reported. I also worked on synthesizing few systems and understanding the phase behavior as it underwent gelation process, and did some scattering study. So I'll be speaking on this topic after a few slides. And lastly, I worked on this industrial system where the agenda was basically to increase the shelf life and performance of the material. So now I'm diving into the topic where I'm going to talk about dynamic arrest on adhesive hard sphere. A brief introduction about the colloidal system and why we want to do this study. So colloidal systems are quite common all around us in a daily life, in industries, in nature. A knowledge about the aggregation behavior of these colloidal systems can be really important in understanding many of the familiar products like paints, personal care products, chocolates, food, and drilling muds. Most of these colloidal systems undergo a process called aging, wherein their properties slowly and continuously evolve as a function of time. The aging behavior is quite evident in food thickening agents, cheese and chocolates as shown over here, where we can see the value of modulus, which is represented by G prime and E double prime, to evolve as a function of time for these materials. It therefore becomes very important to understand the aging behavior of colloidal systems in nature. So with this idea in mind, to understand the aging behavior in colloidal systems to improve the shelf life and performance, we decided to first select a model system to investigate the aging behavior. And we picked up this system, which is a model system of adhesive hard spheres. So the system consists of a spherical particle of silicon of around 30 nanometers in diameter. It is coated with octadecanol, and a TEM image is shown over here. So what happens is a dispersion of these silica particles with octadecanol coating forms a thermoresponsive gel-like systems. So which means that at a higher temperature of something like 40 degree, all the octadecanol chains and the solvent molecules are in disordered state, and it is well homogeneously dispersed in the system, which means that it's in a liquid-like state. Upon decrease in the temperature to temperatures below the room temperatures like 25 degree, the octadecanol chains undergo a disorder to order transition, due to which there is a straightening of the carbon-carbon backbone chain, and it results into very short-range attraction between the particles, and this short-range attraction ultimately results in a gel-like structure at temperatures below the room temperature. So the system is widely investigated in the literature, it's all well established, and this is kind of a phase diagram for the system where the vertical axis tau b represents the attraction strength. Lower the value means more attraction, and phi is the volume fraction of these adhesive hard sphere on the horizontal axis, and it has well been characterized using multiple characterization techniques like rheology, light scattering, neutron scattering, and simulations. And we have a phase diagram which suggests that it can be present in different phases like liquid, gel, or two-phase region, depending upon where it is located on this phase diagram. Now, so a gel is a system which has some interconnected networks in it, and it can be able to withstand its own weight. So that is what we call it, the gel. If you want to know how is it different from a glass, then the perspective would be that a gel forms a percolating network, whereas glass is quite, it's not interconnected in network. It can be either attractive or repulsive, whereas a gel is always attractive in nature. So that is what I call a gel. And rheologically, we have very sacrosanct definitions of gel, which I'll be talking about in a few slides. So while the system is already existing in the literature and it has been investigated what happens upon shallow thermal changes to the system, it is still yet to understand what happens when the system is subjected to deeper thermal quench. So by deep thermal quench means we are giving it a drastic change in temperatures to temperature from like 40 degree, which is like liquid-like state, to temperatures well below the room temperatures. So that is the goal of the work, to understand the rheology and microstructural changes in this model system of adhesive hard spheres upon deeper thermal quench. So now we have a system in hand and we know it is thermoresponsive in nature. So we do a simple experiment to characterize its thermoresponsive nature, and we subject it to a temperature ramp down and then up cycle, and we see the corresponding changes in the modulus value, which is G prime and G double prime as a function of temperature. As evident, initially at the higher temperatures, the value is quite low. It then increases sharply by almost 5 orders of magnitude, suggesting that it undergoes a liquid to a soft solid-like transition. And upon increasing the temperature again, it follows the same cycle. The point of crossover between the G prime and G double prime is often taken as the gel point temperature. But as you can see, the crossover point is slightly different during the heating and the cooling cycle. So in order to have a more well-defined gel point temperature, we seek refuge in the Winter-Chambin criteria. So Professor Henning Winter did some pioneering work on gel-like systems, and he came up with this principle that at the point of critical gel transition, the value of moduli will obey an identical power law scaling behavior on applied frequency, and tan delta, which is basically a ratio of G double prime to G prime, will become independent of frequency. So we do carry out this experiment and see the temperature at which the tan delta becomes independent of frequency and G double prime and G prime obey identical power law scaling, and we characterize that temperature as the critical gel point temperature. So this is the temperature where there is the first instance of forming a percolated network, which means that if we have a system of this adhesive hard sphere and we make a box around it, we'll be able to cross from one part of the box to the other part by just following the path of the connected adhesive hard sphere particles. So this is the temperature at which there is the weakest path spanning percolated network, and we now have a well-defined gel-like temperature, which is 25.4. So the idea of this temperature is only to characterize the gel point temperature. It has to be just interconnected so that it can span the entire space. So if you see in a larger length scale, it will be a mesh-like structure or a honeycomb-like structure, which is all interconnected in nature. I'm just showing, you can see more fingers here because maybe the system is a little dilute. So I'm just trying to, but if you see in a more larger length scale, it will be, if you see a cryotam image, maybe I can share later, it will be more homogeneous and all mesh-like structure, which is well-connected in nature. Yeah, so it's not fingering or instability is something which is occurring here. This is a schematic. Yeah. I have published some cryotam images which is there, but this is just a schematic for nature. So the idea was only to characterize a gel point temperature. So we have a reference temperature that, okay, I have a specific volume fraction of adhesive hard sphere, and this is my gel temperature, so that we can quantify what is a shallow or what is a deep quench for this particular system. So we take the system, put it on a rheometer, and try to give it a shallow thermal quench, which means that we're taking it to a temperature from 40 degree to 25 degree, which is just 0.4 degree below the gel point temperature. We give a step command of change in temperature, but rheometer is not an on and off switch. It takes certain amount of time, which is like 30 to 40 seconds to achieve the target temperature. and the corresponding evolution of modulus is shown over here. We can see that the value is quite low in the initial times, and then it increases, crosses over, and then it shows a slow power, a slow increase with time. This is quite evident in many colloidal polymeric system, which is a typical signature of aging in the system. So this is something which is well established. Now we subject this sample to a deeper thermal quench, where we give it a change in temperature from 40 to 21 degree, which is around 4 degree lesser than the critical gel point temperature, and see the corresponding evolution in modulus. What we see here is the initial part remains the same as the shallow quench, but after the increase, after the slow increase, there is a sudden change in the value of modulus, and the inset over here is basically an enlarged view of what is happening. We see that the G prime undergoes a drop and G double prime undergoes a slight increase, a slight overshoot over here. So this was something which was very interesting to us. This was never reported in the literature. So we wanted to understand what is happening by doing some bulk measurement using rheology. So the first thing which comes to our mind is whether it is repeatable or not. So let's try it at different temperatures below the gel point temperatures. So first we begin to try with different temperature ramp rates at which I change the temperature. So we begin with very slow ramp rates so that we give the system a lot amount of time to restructure, to reorganize, and then take the final state. So when the ramp rate is very slow, which is below 5 degree per minute, we see that such transition is not observed, and the system undergoes a rapid increase, which is signature of liquid to soft solid transition, and then almost insignificant increase. When we make the process of change in temperature quite fast, quite rapid, we see that the system undergoes a drop, and it is observed above a ramp rate of 5 degree per minute. So we characterize the time at which it undergoes the drop and plot that time, which is T star, or we also call it the transition time, as a function of temperature quench ramp rate. So we observe that only after a temperature ramp rate of 5 degree, the system undergoes this typical transition and the value decreases with increase in the quench ramp rate. It shows an exponential behavior, but maybe you can try to fit some other model also to it. There is no theoretical evidence to why it should only behave exponentially. We also see the value of G prime at the end of the aging study, which is a duration of 1 hour, and we see that it falls into two different groups. One is very high value, other one being a slightly lower value. So this basically suggests that we have two domains over here. One where the transition is not occurring when the system is undergoing a very slow process of change in temperature, and the system achieves a very high value of G prime. But at higher quenching ramp rate, the system undergoes this transition, and therefore the G prime value is low. So using this graph, we can transition or differentiate the system into two regions over here. One where it undergoes the transition, and the second one where it doesn't undergo the transition. So after this, we keep the ramp rate constant and change the different temperature at which we do the experiments. So we begin with 23 degree, which is again closer to the 25 degree, which is the gel point temperature. We see that there is a sudden drop in G prime again, which is followed by a slow power law increase over here. So we characterize few features over here, one being the value, maximum value of G prime before the transition, one at the time of transition, and the other value of G prime at the end of the aging study. We again decrease the temperature and do the same study. We see that it undergoes a very sharp decrease in G prime value, and the transition time is noted over this middle graph over here. Epsilon is basically the extent of thermal quench, which is nothing but the difference between the target temperature and the gel point temperature. We further decrease the temperature to like 12 degree, and what we observe is that this transition is no longer sharp now. It's something, some resistance is occurring to the transition, due to which it takes finite amount of time to undergo this transition. But the overall take-home message is that it does undergo the transition when you change the temperature drastically to temperatures well below the gel point temperature. The transition temperature over here can be seen to obey a non-monotonic trend with extended thermal quench. We believe that this is due to two contradictory forces acting into play. One, when we decrease the temperature suddenly to very low temperatures, the system dynamics is getting more and more arrested, which would not allow, or which would not like this transition to happen. But at the same time, the driving force for this transition is also increasing, which would encourage this transition to occur. So as a result of this interplay between the two competing effects, there is a non-monotonic trend in the transition temperature. So based on the rheological findings, we try to anticipate what might be happening at the microstructural level and how will the system walk upon on the phase diagram over here. So this is a schematic picture which is trying to mention how the system would be spanning the entire phase space. So when we are at shallow thermal quench, we are in the gel-like region, but as we decrease the temperature, we have sudden decrease followed by slight increase, which suggests a nucleation and growth-like dynamics, which suggests that the system might be in the binodal region. As we further increase the extent of thermal quench, there is a sudden decrease in G prime followed by almost insignificant increase, which suggests a very instantaneous transformation like spinodal decomposition. At further lower temperatures like 12 degree, the transition is no longer sharp, which suggests that we are entering into the deep two-phase region where the glass line might be intersecting the two-phase line, and therefore the system dynamics is becoming more and more complex. So this is a brief understanding which we gain from the rheological study. We now go to do some neutron scattering experiments to gain the actual microstructural insights of what is happening to the system upon deeper thermal quench. So we do the experiments at Oak Ridge National Laboratory where we use an Anton pyriometer, and we do the similar experiment where we give the system a sudden temperature shock from 40 to 21 degree, which is the target temperature over here, and we collect the intensity of the scattered light, scattered neutrons as a function of Q, and we plot it as a function of different time intervals. As aging proceeds, how does the intensity curves shift? So initially at 40 degree, the curves are almost on top of each other, but as we subject it to a temperature change, the intensity curves grows and it gains value over here. So we are not the first one to do scattering on this system. It has already been done in the literature, but has been done for shallow thermal quenches, and the data is reported over here from the literature. We can see that the graph is quite similar, that where the intensity is gaining value with respect to time. Other thing to note over here is that there is a low Q scattering, upturn in the scattering, which has not been yet modeled in the literature, and people were not able to find out the reason behind this low Q upturn over here. So we tried to address both the points to understand the microstructural changes at deeper thermal quench and to understand the reason for the low Q small upturn at low upturn in the scattering value. So we use the sticky hard sphere model, which is commonly used to model the attractive system, and we did the simulation and we did the fitting using SAS view. Here is a snapshot of how SAS view looks. It might look very complex, but it's not that complex. I'm just trying to explain what are the different components which we have used to model the scattering data over here. First is the form factor, which contains the information of the size of your particle, which you already know beforehand, and you can also gain insight from micrography or images. We then use the structure factor, which is of sticky hard sphere in nature, and we get a parameter which is stickiness. Stickiness is the same parameter as tau, which was on the vertical axis of the phase diagram over here. And lastly, we also add a small fractal model to it. And using this fractal, so if we use only the form factor and the sticky hard sphere model, we get the red curve over here. But as you can see, the red curve is doing a great job in fitting the attractive strength and the high Q data, but the low Q data it's not able to fit. So we add a fractal model to it, which suggests that we have very small volume fraction of fractals present in the systems, which are quite ubiquitous in nature. So these fractals are basically fractal aggregates which are present in the form of impurities in the system, or you can say that it's always ubiquitous in nature in the system over here. And with addition of this fractal model, we are now able to get a very good fitting to the entire experimental data during the aging time. Now, this is all good and this all works when we are at the early times. What happens when after the transition? We try to use the same analogy to fit the scattering data, but irrespective of any change in the fitting parameters, we're not able to fit it. So next what we try is the volume fraction of the system is fixed at 0.2. We try to increase the volume fraction a bit, which is from 0.2 to 0.35, and we say that we now get a very nice fit between the experimental data and the model using the volume fraction when increased to 0.35. So this suggests that Maybe at the microstructural level, the system is phase separating into colloidal rich and colloidal lean regions, due to which the volume fraction locally is increased, and therefore a higher volume fraction of 0.35 is now able to predict the experimental data well. So therefore, the scattering data also suggests that locally there is an increase in the volume fraction, and it's the interconnection between the colloid rich phases which leads to the viscoelasticity in the material. So using the fitting parameters, we are able to get a relationship between how the rheological parameters vary and how the fitting parameters of the scattering study varies, which suggests that it's well in hand. At the time where the rheological shows a transition, we have a sudden change in the local volume fraction from 0.2 to 0.35, and it matches well with the scattering study. We also try to investigate if these type of transition can occur when we give it a shear rejuvenation to the sample. So what we do is we take the sample, keep it at a target temperature below the gel point temperature, and shear melt it vigorously to see if the system can again undergo this transition or not. But to a surprise, if you keep on thermally rejuvenating the sample by taking it back to 40 and cycling it up and down again, the system is very much reversible, which is the black and the green symbols. It undergoes the transition. But if you shear melt it at a temperature below the gel point temperature, the transition is no longer observed. The value of modulus is insignificantly growing with time. So this suggests that shear rejuvenation cannot take your sample back to the initial state as a thermal rejuvenation could do it. We also did the scattering SANS experiment to confirm that, and we saw that the intensity curves for thermal rejuvenation and for shear rejuvenation are not identical, which suggests that there is some kind of structure still retained even though you apply very high amount of shearing to the sample. So it's only the thermal rejuvenation which takes the sample back to the initial state, and therefore the transition can be occurring again and again. So with this rheological insights and microstructural insights from neutron scattering, we are now able to understand what is happening to this model system of adhesive hard sphere. At 40 degree, it's at very nicely well homogenized state. As you keep on decreasing the temperature to like critical temperature, we have a weakest or a single path which connects all the particle, and it forms space spanning populated network. As you further decrease the temperature, we enter into the two-phase region where the system forms colloid rich and lean phases, and these colloid rich phases are interconnected by few particles, which leads to the viscoelasticity in the material. As we go further down and decrease the temperature and extent of thermal quench, we enter the two-phase region where we have very rich colloidal rich region, and we need to more understand in that region. So this is what our finding was, and surprisingly, at the same time when our work was published, there was another group who was doing some dynamic simulations, and they came up with a similar idea for a different nanoemulsion system, and they suggested that with change in temperature, the system can span different structures and can form this colloid rich and colloid lean phases in the system over here. So we suggest that our study of rheology and SANS study is a nice proof that the system is undergoing phase separation and entering into the two-phase region, which is also supported by the simulation study in the literature. But we'll be happy to do some more simulation study on this work exactly. So with that, I would like to just summarize the work. We had a system of adhesive hard spheres, which is consisting of silica particles of sphere in shape. We saw that when we take it to a very deep thermal quench, it undergoes a very rapid transition. And this transition is maybe because it is entering the two-phase region. We got some insights from doing neutron scattering that locally that there is an increase in the volume fraction, which suggests that there is formation of colloid rich and lean phases. And the basic take-home message from this work is you can use rheology as one of the first technique to understand your system and to gain some insights which can be used to design some more delicate and costly beam type experiments. So that is the basic take-home message from here. Although we understand many things, there are yet many things for us to explore, and we don't know why is that occurring. Like, why is 5 degree per minute the critical ramp rate above which the transition is occurring, and why is it not occurring before that? Is there any critical time scale of the material which we can utilize to non-dimensionalize the transition time and come up with a non-dimensional time for that? So these are the few questions which we don't understand. This part of work was done with Professor Norman Wagner at University of Delaware during my postdoc, and the funding came from NIST Center for Neutron Research. So this is what I did recently, and this is what I plan to do at IIT Madras. So this is a research theme of my lab, what it would look like. So the idea is basically to understand the microstructure and viscoelasticity of colloidal dispersion. So it's going to be one-stop understanding of all colloidal dispersions. So we begin with controlled synthesis of particles which of varying shapes and sizes, and do a very nice characterization using multiple characterization techniques like rheology, scattering, images, DSC, and then understand the reason for their experimental behavior to gain understanding and have a very nice idea about the performance, the characteristic behavior of these colloidal dispersions. So these colloidal dispersions would, on one hand, result in some academic knowledge which can be used by other theoreticians to understand their simulation study and gain some collaboration. While this understanding can also be used in many industries because these thermoresponsive systems and many other systems are widely used as drug delivery agents or in household products. So it will also have some industrial implications as well. So that would be the theme of my work, and hopefully next time I would be presenting some work from my very own students and group. So yeah, happy to be here, and with that I would like to take any questions.
You had a slide where you were fitting it to phi equal to 0.35.
Right.
As a, can we just go back? Yes. So I was just very curious, this fitting, is it that parameter value? Is it a fitting value, or in your experiments, I do not know what technique would be used, but is there a technique to actually see what is the volume fraction that will actually fit that, by which you would know the local density of the colloid-rich phase? I just want to know, is it a fitting parameter, or is it something actually correlates with what you see in your...
So in an ideal world, we would not use volume fraction as a fitting parameter because volume fraction is something which we already know, like the diameter of the particle or the thickness of the particle, length of the particle. So these are the few parameters which we usually don't use as a fitting parameter because that's like the first principle. You cannot change these parameters. But since in our case, we were anticipating that the system would undergo a phase transition to form some colloid-rich regions. So only for that part, we tried to use volume fraction as a fitting parameter. So you just click on volume fraction as one of the fitting parameters, and we tried to change that parameter. So it increased, and then we use volume fraction as a fitting parameter. So ideally we would not do, because we know that if we have a system mass is conserved, the system should remain, the total volume fraction still remains the same. The number of particles still remains the same. It's only locally that the volume fraction is increasing, and therefore I use it as a fitting parameter.
Why I've asked the question is that, is it, if in a simulation kind of setup, is it not possible to measure local densities and then see what is the local density? And you don't have to use a fitting parameter, but I measure the local density and see what volume fraction may correspond to that, and thereby get also an idea of what is the local density that is happening. Is that possible, or it's not?
From the experiments, it's not possible to say that, but yes, I understand that using simulations, it will be possible, and we'll have one fixed number which will correspond to that low increased density over there. But here we just had an idea that there is an increased density, which would not be an insignificantly large number, a significantly large number, but something closer to the value. So because it's only a local increased, so we used just as a guess number over as just.
One last question. Sure. We were talking about this anisotropic particle. Suppose if instead of hard spheres, one has hard rods, or these kind of other shapes, would you? What is your guess? Would these results would be different, or the rheological properties would be different? What is the expectation?
Yes. So this transition, it's very novel and unique. It's not observed yet. So we anticipate that this was because the spheres had more degree of freedom in the terms that was able to diffuse, rearrange, and span the space easily, due to which it was able to undergo this transition and fall from a very homogeneous arrangement to a spatially heterogeneous arrangement. What would happen in case of rods? What I anticipate is rods would interact in many different ways like spheres do. Like spheres would have identical interaction irrespective of where they contact, right? But sphere, if it is interacting in this way, they will have a very strong attraction, and therefore it will be very difficult for them to rearrange and diffuse. And rods can have multiple types of attraction, one being this, which is very strong, other being T-shaped or some this shape. So in case of hard rod system, I would expect that the degree of extent to diffuse or the extent to reorganize itself would be difficult, and therefore it won't be easy for that system to undergo the same transition at the same temperatures. Maybe under some very extreme conditions, it can undergo that transition, but it wouldn't be that easy just because it doesn't have that degree of reorganization or mobility in the system.
Perhaps multiple time scales also.
Yes. Yeah. And diffusivity, rotational and directional, so it would be different.
Correct. I have a couple of questions.
Sure.
So the first question is related to the shape, what she was talking about. But my question is, if you know the properties of the nanoparticle changes when the size changes.
Right.
So the interesting, the transition, what you were talking about, is it size dependent? Have you checked, whether the smaller size or maybe the bigger size than this one?
Unfortunately, I have not changed the particle diameter. I have changed the volume fraction only to see if it occurs, and it occurs at different volume fraction at this same fixed diameter. I haven't explored different diameter, but for a sphere of maybe not very big, like this is 30 nanometers, for 100 nanometers also I would expect the same. Maybe at different temperatures, the quantitative value will be different, but the transition would still remain there.
Okay. So the second question is, it's very nice that rheological data, and then you extracted the structural rearrangement from higher temperature to lower temperature.
Right.
But have you tried the electron microscopic pictures and then freezing drying the samples at that temperature? 4 or 5 temperatures, 40, 45, 42, 43, 47, something. So have you correlated your results from the rheology, and then whether it is matching with the electron microscope? Because you said that isotropic first, and then when the temperature goes down, and the random is actually kind of things.
We haven't been able to do that, but yeah, that's a very nice idea to get a very good confirmation about what we are proposing is occurring or not. But we haven't been able to do that yet. But I'm sure some other student in the group who is continuing my work will definitely try to do that.
Actually, I have a couple of questions. So, you are getting it nice fitting at 0.35 volume fraction. What if you further increase the volume fraction? What kind of fitting you will get?
So fitting deviates from the experimental data.
Deviate from the...
Right.
And the second is like, this is a hard sphere. If you microgel particle like soft sphere, right? So mostly that is also temperature dependent. And you are getting the transition just around 27, 28. That is critical for microgel particles. So what kind of behavior you will expect, like percolating method or something, if you use?
So it also, microgel particles, if the same transition would be observed or not is what your question is, right? So obviously it's very specific to the system and under what conditions you're doing this study, which results into certain kind of transition, or else it would have been ubiquitous in the literature till now, right? So depending upon the attraction strength also between the microgel particles, as I said, like for the rod particles, if the attraction strength is very large and it wouldn't allow the particles to rearrange by itself, then it would be difficult for the same system to undergo the transition. So it depends upon a lot of factors which results into this. So these are like very short range attractions. So attraction becomes important only when it's very near to the particles, and therefore it can have multiple times it can arrange, contact, and then contact again. So if the attraction is very strong in your system, it will be very difficult to rearrange, diffuse, reorganize to have this kind of transition. This is what I expect. Yes. Thank you.
So I have a question, like actually from the structure factor, actually it should be related with the electron density, right? So can we not know the electron density of this?
Maybe we can go to the electron density, but I don't go in atomistic level to gain the understanding. I normally, the kind of study and we gain insight at more mesoscopic level is what I would say. I haven't been able to explore the atomistic level, and but I'll be happy to collaborate and gain insight on how to gain the electron
Yeah,
density
so
insight.
in the sorry, in the fitting this SAS view, so we will have a fit parameter of electron density.
No, I don't have a fit parameter of electron density. I only have attraction strength, which is like a collective term for interaction between the particles. So we don't go to the atomistic level to the electron density.
Thank you.
So ma'am, these C18 nanoparticles, are they dispersed in water or in some organic solvent?
So it's an organic solvent which is tetradecane. So we need to have specific kind of solvent in which the octadecanol chains would undergo the disorder to order transition. So any linear alkane solvent can work over here. So this is not water. This is in particular in tetradecane. You can use any other alkane solvent solvent to use that, and this would work.
So are the gels stable enough if you overturn the vial in which the gel is, or will it be just stable, or is it just a very highly viscous solution?
So it's really able to withstand its own weight. So you can imagine it's a strong gel. Yes, at temperatures below the room temperatures. At 40 degrees, it's very easily flowing, and it remains stable up to years. So yeah, it's a good system to work with. You once synthesize the system, and you just keep on doing experiments. Its thermal rejuvenation can work, so you can work again and again on the same batch of samples. So it's easy in that way to work with.